Good morning, everyone. I'm a PhD student in materials chemistry at Biscay University. It's a good pleasure and honor for being a part in the first international conference on sustainable energy and advanced materials to represent my research, which is titled Synthesis and Electrocatalytic Properties of Zinc-Doped Lanthanum Cobaltite Perovskite Type Oxide. So what I have here, it's a quick slide overviewing some technology about hydrogen and oxygen cycle that starts with the free and the clean energy to split water into oxygen and hydrogen. And after this fuel's made, we need some ways to convert them to electricity, and that is the fuel cell aspect. So how can we split water into oxygen and hydrogen gas? In this kind of system, we have two different electrodes, anode and cathode. And if we were to do the electrolysis in alkaline solution, at the anode side, we can take hydroxyl ions and convert that into oxygen and electrons, where the electrons can then travel to the cathode side and reduce water to hydrogen gas. But the problematic is the oxygen evolution reaction side, where the reaction is typically the slower. So here we have activity, how good the catalyst is as function of stability of anode catalyst. As we increase the activity, the stability decrease. So the really problematic is how can we increase the activity and the stability at the same time? This is the key challenge. Typically, iridium and ruthenium oxides are often used as catalysts toward oxygen evolution reaction because they have the best catalytic activity but the less stability in addition to scarcity and high cost, while the perovskite type oxide with general formula AbO3 have a high catalytic activity, good stability, abundance, and low cost. Also, the partial substitution of A and or B site can improve the catalytic activity. So through these advantages, zinc-doped lanthanum cobaltite were prepared using a sol-gel method. So as shown in the chart, metal nitrates were first dissolved in ethanol separately, while the citric acid was added to the mixture under stirring at about 80 degrees Celsius until the formation of the gel. Thereafter, the gel was dried at 100 degrees Celsius and then calcined at different calcination temperatures. The characterization of the catalyst has been studied by several techniques, such as thermogravimetric, differential thermal analysis, X-ray diffraction, Fourier transform infrared spectroscopy, scanning electron microscopy, and electrochemical measurements. The electrochemical measurements were accomplished by through electrodes method, where the simple serving as working electrode, AgAgCl, which is the reference electrode, and the platinum as a counter electrode in alkaline solution. Result and discussion. Figure 2 shows the Tg and dTA curves of the dried catalyst. The Tg curve exhibits that the decomposition reaction can be divided into four parts. The first weight loss related with a broad endothermic and sharp exothermic process can be ascribed to the removal of the remaining water and the partial decomposition of citric acid. The second mass loss accompanied with a broad endothermic peak may be assigned to the transformation of the citrate to aconitate. The third mass loss associated with an endothermic process corresponds probably to some organic metal complex reactions with escaping some gas like CO2. The last weight loss involves two endothermic peaks, can be attributed to the formation of lanthanum cobaltate perovskite type oxide. Figure 3 shows the XRD patterns of the catalyst calcined at different calcination temperatures. After being subjected to a temperature of 800 degrees Celsius, the XRD patterns reveal the formation of lanthanum cobaltate in addition to some weak peaks due to the secondary phase. These results reconfirm the last two endothermic peaks in DTA curve. The peaks of the secondary phase become smaller as the temperature increases. Then they disappear at 1100 degrees Celsius. At this temperature, a pure rhombohedral lanthanum cobaltate perovskite has formed. Figure 4 exhibits the XRD patterns of the catalyst with different X values. The patterns where X ranging between 0 to 0.3 exhibit a pure rhombohedral structure. As the X increase to 0.4, new peaks appear, where they could be indexed to zinc oxide and zinc lanthanum oxide. This result confirmed that the substitution of cobalt by zinc is achieved at X less than 0.4. The next figure reports the infrared spectra of the simples with different X values. All spectra are rather similar. The infrared bands found at 415, 555, and 595 cm-1 can be assigned to the metal-oxygen stretching vibration of octahedral coordinated MO6. The weak absorption bands appeared between 1110 and 1728 cm-1, which they most likely correspond to the vibration of the perovskite crystal lattice. These results reconfirm the formation of the perovskite structure and support the result found in the X-ray diffraction. Figure 6 depicts some images of the catalyst. It is interesting to note that the morphology of the simples are almost identical, and the texture of the surface seems to consist of microagglomeration of nanocrystallite particles with different shapes and sizes, in addition to uneven distribution. Figure 7 shows the linear sweep voltammetry of the catalyst in alkaline solution at scan rate of 50 mV per second. As we can see, a wide range of performance just by introducing zinc in the lanthanum cobaltate structure, and the activity is highest for X equals 0.1, and then it is lowest for the endoped one, followed by X equals 0.2, and then X equals 0.3. On the other hand, the substitution of zinc allowed to raise the current density, which is approximately 1/2 time higher for X equals 0.1 than endoped one at 0.6 volt. Conclusion: zinc-doped lanthanum cobaltate catalysts were successfully prepared using the sol-gel method. TG and BTA analysis show the thermochemical behavior of the simples. XRD and infrared spectroscopy analysis enabled us to show the presence of the pure perovskite structure at 1100 degrees Celsius. Scanning electron microscopy shows that different shapes and sizes of particles are formed with very well pronounced agglomeration. The electrochemical studies indicate that zinc-doped lanthanum cobaltate with X equals 0.1 is the best electrocatalyst for oxygen evolution reaction. Thank you for your attention.